pressure is lost, then that pressure pushes the sodium out, and now we have a leakage port for the neutrons to come out, so it's a negative reactivity. So we put some of these in there, and by golly, they actually worked. And I remember vividly, of course, we did these tests bit by bit by bit, you know, kind of thing. But the last test that was done, the reactor was operating at 200 megawatts, 50% power. I was late for the test. And I remember on the PA system, the countdown was coming, 10, 9, 8. And all of a sudden, I had these flashbacks of standing before these regulatory bodies arguing what would happen. If this accident happened in FFTF, we've got a real mess on our hands. And we were actually conducting this test real live. And of course, the reactor responded to shut itself down just exactly as we expected. But it was sort of, my feeling was we've come a long way, baby.
And the loss of power test, first time ever.
Yeah.
Perfectly.
Yeah. Very.
Self shutdown.
These are neat systems. I opened this by saying that people think that these reactors are somehow intrinsically unsafe. They are not. They are probably one of the safest machines that one can build. And I would think, Bruce, on the operations here, you might have answered. My impression in talking to the operators who came out of the Navy, of the water system, said they would far rather run a fast reactor than one of those water reactors. This was the people I talked to. I know John Sackett said this, that the operators over at EBR2, these machines are really fun to run. They're very safe and very controllable.
Even the bargaining unit maintenance people felt that way.
Yeah.
People applied to get into FFTF to do maintenance work.
Yeah.
Wow. Thank you, fellas, for the comments that are there. For me, it was an inspiring period of my life to build an organization, have it turn out with a success in this manner. It was a pure joy. Working with Chuck and the rest of the DOE people was pure joy too. There was a balance. The project had a balance. There was no agency that ruled over the other agencies as all powerful. I don't care if it's safety or if it's quality assurance or what. There was a balance. One other comment to indicate the rigor. We used to have mistakes, and they were called incidents, and we had incident reports to issue. Mm-hmm. We're pretty good at writing incident reports. But incident reports are big ones. You make a big mistake, you write an incident report. But if you get a close call, nobody hears about it. But that bothered me because I wanted to learn from the close calls. And so I put it into effect a ruling that we'd write an information report. Not an incident report, but an information report, a close call report. And we did that, and there were more of these issued than any incident report number. We made good use of it. We learned from our close calls. Okay, I think we're done with this one.
And now we'll hit the, you got a feel for how the organizations work together, and I think the accomplishments of them, right up to the end of the operation of FFTF.
I think DOE brought that about.
The information reports.
No, the way we work together.
The way we work together, yes.
The balancing and the teamwork.
The balancing the teamwork, I agree with that, yes, definitely, yes. So now we'll hit our last topic area, number 7, which is the documentation associated with design, build, and operation of the reactor plant. And we'll start off with our senior representative from the client shop here, Chuck.
Well, these points have been alluded to before in the discussion, but the point is the formalized engineering system descriptions maintained current by HEDL and carefully developed and carefully approved, technically approved operating procedures based on the system design descriptions are part of the key to making this successful. The system descriptions originated with the engineering groups in Westinghouse, approved by AEC headquarters, and then were maintained current by the HEDL operating organization, or HEDL operating engineering organization. The development of operating procedures was carried out by the operators but following the design and the precepts of the design prescriptions and design descriptions and the operating procedures were then approved by the field engineering group, and any changes thereto went through the same process. So that you had throughout the life of the project, you had a discipline, control of the procedures to be followed in operating the plant. An engineering discipline that carried through. It was very important to maintain the success of the plant. That's my point on that.
And we made it very clear from the start that the operations organization would be responsible for the configuration control of the whole plant, no matter what took place. They did it through control of drawings. Going to the test program, every test was concluded with a test certification process that all of the faults had been corrected, or listed the uncorrected faults, the problems that were uncovered by the test, that all the test papers were in place. We overlaid on top of that with the project organization a senior review of the results review. The results review committee took all of these test certifications and checked whether they were valid or not. If there were unfinished, uncorrected fault conditions, change notices required, they were documented through the drawings thereafter. The drawings for the plant always were handled with any change notices to them attached. They were never handled as the old out-of-date drawing. They always gave you the ECNs, the change notices, engineering change notice, along with the drawing. And as they gradually incorporated the change notice into the drawing, then they would have a new drawing to provide. So there was a very severe rigor applied to the control of the configuration of the plant through the drawings, with operations in the lead. That is to say that things like the system design document, system design report, which was the original design concept, you'd like to have kept that intact as well as the guideline for the plant. That became obsolete in the test program. And we chose not to try to go for keeping it exactly current, but instead use the drawings as a preferred option. And that was in fact used. The use of ECNs to document all changes was carefully maintained. It required a huge amount of effort to do it that way. When the results review committee completed looking at all the tests that had been done, they were able to validate to the management that the test program had been completed successfully and were done. So one other comment to make: this verification testing is required for all plant operations, calibrations, compliance, inspections, and what have you. Preventive maintenance, you must do a compliance check, a verification test after you get done doing the work. The documentation is all maintained, it's audited, and that's, again, the operations team has a very good discipline for that kind of control. So we felt very good that they had followed the system. That concludes the remarks I would make on this section. I think that'll cover it well enough.
Yes, and Alan, would you care to add something?
Well,
here?
The lesson learned
Excuse me,
is,
Bruce, I'm sorry.
excuse me, the lesson learned is for the operations organization to be coached that they understand how they are to achieve this perfection, and then turn them loose and require it, audit it.
Which leads right into what maybe comment I was going to make, perfection, you know. The question is, sometimes it's possible to sort of be a little bit inbred and say, you know, how great we are and so forth. But the reality is, to some extent, how are you judged by others? You know, it's kind of a relative thing in some sense. And you might, I'm sure everyone here remembers, in 1979 we had the 3 Mile Island accident. And as a result of that, the industry at large, at least in the United States, formed INPO, Institute of Nuclear Power Operations, where they really encourage all utilities to share, to be more transparent, to share those lessons learned. And Bruce, you referred earlier to, you know, it's not just incidents, it's close calls, those kinds of things. What can we learn from each other? So the project here decided to join INPO, even though this is not a commercial reactor, but basically, how do we here at FFTF, how do we stack up against the commercial reactors? And interestingly enough, the plant availability, as I recall, for FFTF was higher than most of the commercial plants, recognizing that this plant was expected to be routinely shut down on many occasions, to put experiments in, to take experiments out. After all, it was a test machine, not a power reactor, for the purpose of producing electricity. It didn't even have a turbine or a generator. It was a materials test reactor. But the plant availability was very, very high, and it was largely, I think, due again to the discipline, the documentation. Everything was very, very carefully controlled and relayed. So that was kind of it was really, I think, interesting to see how this reactor operated under those, shall we say, the national lens. The other factor that I'm not sure, you know, the reactor operated very, very successfully for 10 years and really produced marvelous results. It was shut down not because it was obsolete in any such imagination, but because it lost its mission in the eyes of the Department of Energy. A lot of discussion has taken place since that time. Well, could the reactor be restarted? You know, it's very difficult to see in some minds how you could do that, because if it doesn't have a mission, of course, it wouldn't be restarted. But the question came up a few years ago, and it's still a lingering question. Now that there is an interest worldwide in fast spectrum reactors, not so much for breeding, because we have found a lot more uranium than we thought was the case at the time FFTF was built, but because of waste transportation. We know that at Yucca Mountain, the higher actinides cause a heat load that limits the loading, and fast reactors can eat up those actinides, like pouring warm milk in front of a puppy dog kind of thing. It's good fuel. Now Yucca Mountain's been taken off the table, so what do we do with our waste? Well, a fast spectrum reactor is recognized internationally as one of the solutions. So the question comes up, is it conceivable that FFTF could be restarted? And of course, people say, well, you know, there's politics involved and so forth. But the question, technically, can it be restarted? A couple of years ago, the Department of Energy did fund a study. It was a short study, about a 2-week study, where we pulled in a lot of the people who built the plant, who operated the plant, to see if it could be technically restarted. And it was interesting that most people came in kicking and dragging, oh my God, how could we possibly do this? We would have to take the instrument tree out, we'd have to clean out the sodium and so forth. Yes, but we could do it. And the conclusion was unanimous. Yes, technically it could be restarted. And part of the reason for that is because the documentation is done so well. Not only in building the reactor, but in fact in starting to dismantle various systems. Everything has been very, very carefully documented, so that even from a regulatory standpoint, those records are all there. And I think this is, again, a testimony to the discipline and to the value of that documentation. If somehow the stars and the moon should align themselves for a possible restart, we could do it with this reactor just because of the discipline in documenting it and being so very, very careful at every step of the way. And I think this is a real asset.
Well, Bruce mentioned drawings, and as I think I said a little earlier, FFTF is highly documented. We've got possibly over 65,000 drawings that exist out there for the FFTF plant itself. We did keep most of those drawings up to date. As the reactor shut down, and then as we started going into total shutdown and those kinds of things, we used a graded approach to determine how we maintained those things. And the drawings were divided into what we called essential drawings and support drawings, and then general drawings. Essential drawings, back when the plant was operating, we possibly had in the order of 2,500 to 3,000 essential drawings. An essential drawing, what that means is that as changes are made that affect that drawing, when the change is implemented in the field, as it's documented that it's implemented in the field, the ECN goes into the file along with the drawing, and we have then 30 days to actually physically change the drawing so that the drawing is totally updated. Support drawings are a little lesser category, and those we said, well, we could stand to have a number of changes against those drawings before we really needed to incorporate them into the drawings. And so those were identified and said, well, we could have 5 or 6 changes, and then we would go ahead and start incorporating changes into the drawings. As the plant was under operation, there was a system called station files. Station files were file cabinets that had copies of all of the drawings that were deemed to be appropriate for that area. For instance, a control room had a station file in there, and all of the drawings that were essential were in that file, and a few other drawings besides that were determined to be appropriate, so that they were readily available. The operators did not have to go over to a drawing vault and request a copy of the drawing. They had it right there. All they had to do was jump into their file, pull it out, lay it out, and take a look at it and determine what to go do. Now, configuration control is always an interesting topic when you get into it, and one of the things that I think, a point that I'd like to make in regard to drawings is that you need to keep an adequate number of